Now, if a force actually is conservative, in this video I want to talk about what you can do with that mathematically. So if a force is conservative, then it actually makes sense to define a potential energy associated with that force. So in the cases where it's conservative, you can actually talk about what the potential energy is that's stored in the interaction. In the cases where it's not conservative, it simply doesn't make sense to talk about a potential energy associated with the interaction. So let me sort of explain why that makes sense physically. If I sort of imagine I've got some force field, right? So let's say the force field looks like this. And I'm going to choose some point in this force field to be what I'm going to call my origin point. And I'm going to label that with an O as my origin. Once I've defined that point to be the origin, if this is a conservative force field, I can actually ask the question, how much work is required to move an object or to move the object of interest from the origin to any other point in this force field, right? So I could think about going to this point, right? So let's actually, say that we've got, I'm going to just choose a different actual origin for the coordinate system. So this point O is just the point at which my potential energy is 0, as opposed to the origin of my coordinate system. And I'm going to ask the question, how much work does it take me to move the object of interest from point O to some final point? Let's say point A. Well, since it's conservative, it doesn't actually matter what path I choose. I could go from O to A this way, right? I could go from O to A along this path, right? Every one of them should give me the same answer. And so the way that I'm going to define my potential energy is I'm going to say the potential energy of this that's stored in this interaction is a function of position, right? And that potential energy is actually the amount of work that's required or that I have to do against the force. So a negative sign for against the force to go from my original point to the point that I'm interested in. Okay. So let's think about what that means in this case, and let's try to figure out whether the potential energy at point A is positive or negative. So to go from this O point to point A, let's say I follow this path. I'm going to walk along this part, right? This part requires 0 work because I'm walking in a path that is perpendicular to the force. And then to go from here to here, the force is actually doing negative work on me as I go from here to here. In other words, I'm having to put work into the system. I'm pushing against this force in order to get up to point A. So here, the work that the force is doing is less than 0. The work that I am doing to get it there is greater than 0. And the potential energy is the work that the force does, right? Not the work that I do. So this is actually the potential energy at point A is going to be greater than 0. Okay? So let's do a sort of concrete example of that. Let's imagine I have a mass that's on a spring, right? I'm going to define the point x equals 0 where the spring is relaxed to be my origin point, and I'm going to ask the question, how much potential energy is stored in the spring if I stretch the spring from x equals 0 to x equals L, right? Well, my force that the spring is going to exert is simply going to be minus k times x, right? Because if x is equal to 0 is the rest length, as I move the spring to the right, the force is going to be to the left. It'll be minus k times x in the I hat direction, right? And notice that that force does depend only on position, so it looks like it could be a conservative force. In fact, if you think through this, the spring force is a conservative force. So my potential energy then at some point x, right, is going to be the integral from my origin point, that is x equals 0, to the point that I'm interested in, which is L, right? So this is actually the potential at point L, of minus kx times I hat dot dx I hat, because dx will be this differential length that I'm moving through. And so not surprisingly, that force, so the force is negative k times x. I need to pick up this extra negative sign out front. So I get the integral from 0 to L of kx dx, or the answer that you already knew before I started this, probably the potential energy is 1/2 kx squared. So as I stretch this spring, the amount of energy that's stored in the spring goes up as the square.